We've been sold a dream, moon bases, lunar cities, humanity among the stars. But there's a gap between the vision and reality so massive it could derail everything. The moon isn't a stepping stone to the stars. It's a cosmic death trap wrapped in beauty. And the more we learn, the more terrifying it becomes. And here is a question. If you could only bring one item from Earth to help you survive on the moon, what would it be and why? Comment down below. I will pin the most creative answer. Now let's begin. The moon has captivated humanity for millennia. Ancient civilizations worshipped it. Poets wrote odes to its beauty. And in 1969, we finally touched it. Neil Armstrong's boot print became one of the most iconic images in human history. But that boot print revealed something sinister, something that would haunt mission planners for decades: lunar dust. You see, when we think about space colonization, we imagine gleaming habitats, astronauts bounding across alien landscapes, and the triumph of human ingenuity. But the reality, it's far more brutal. The moon isn't just a barren rock, it's an active threat to human survival. Every grain of dust, every moment of exposure to cosmic radiation, every sunset that brings temperatures plummeting to -173 degrees Celsius, it all conspires against us. Let's talk about what we've learned from real missions. The Apollo program wasn't just about planting flags and collecting rocks. It was our first real encounter with lunar conditions. Astronauts from Apollo missions 11 through 17 all reported the same bizarre phenomenon. Lunar dust got everywhere. It coated their suits. It infiltrated their spacecraft. One astronaut, Harrison Schmitt from Apollo 17, experienced what he called lunar hay fever after inhaling particles that had made their way into the cabin. His nose felt like it was on fire. His throat became irritated. This wasn't ordinary dust. Here's where it gets fascinating and frightening at the same time. Lunar dust particles are nothing like Earth dust. On our planet, wind and water erosion gradually smooths particles over millions of years. But the moon has no atmosphere, no weather, no gentle polishing forces. Instead, micrometeorites constantly bombard the surface at speeds exceeding 11 kilometers per second, shattering rocks into jagged, glass-like shards. Under a microscope, lunar dust looks like microscopic razor blades. NASA scientists have spent years studying samples brought back by Apollo astronauts. What they discovered would make any doctor's blood run cold. When human lung cells are exposed to lunar dust simulants in laboratory conditions, something deeply disturbing happens. The dust particles are so sharp and so reactive that they slice through cell membranes. They trigger oxidative stress, essentially causing cells to rust from the inside out. Reactive oxygen species surge through tissue. DNA begins to break down. The immune system goes haywire. Research published in 2024 showed that human lung epithelial cells exposed to lunar dust simulants experienced significant damage within just 24 hours. Necrosis, that's cell death, occurred in respiratory cells. Early apoptosis, programmed cell suicide, appeared in blood cells. Even more concerning, genes responsible for immune response and inflammation, genes with names like CXCL1 and SPP1, showed dramatic changes in expression. This isn't just irritation. This is fundamental biological damage at the molecular level. But wait, there's more to this nightmare. The dust problem isn't just about what happens when you breathe it in. Lunar dust is electrostatically charged because of constant bombardment by solar wind and ultraviolet radiation. Without an atmosphere to dissipate these charges, dust particles cling to absolutely everything. Spacesuits, equipment, solar panels, seals on airlocks. During the Apollo missions, this caused serious operational problems. Dust worked its way into mechanical joints, causing excessive wear. It scratched helmet visors, reducing visibility. It even compromised the integrity of environmental seals. Imagine trying to build a permanent base when your equipment is constantly being coated in abrasive, toxic, electrostatically charged particles that you can't simply wash away. There's no water on the moon's surface to rinse things off, and even if there were, the dust's unique properties make it incredibly difficult to remove. Engineers have tested numerous cleaning methods, from mechanical brushes to electron beams to special coatings, and none provide a perfect solution. Now, here's something most people don't realize. The moon has been collecting cosmic secrets in its soil for over 4 billion years. Unlike Earth, where plate tectonics constantly recycle the surface and weather erodes everything, the moon's surface is like a cosmic archive. But that archive contains some truly dangerous materials. In permanently shadowed craters near the lunar poles, regions that haven't seen sunlight in billions of years, scientists have detected not just water ice, but also trapped volatile compounds. Some of these volatiles could be toxic. We're talking about substances that have been accumulating for eons, frozen in place, waiting for human excavation to release them. Speaking of which, let me tell you about an incredible resource that goes deeper into observing celestial bodies from your own backyard. If you're as fascinated by space as I am, you need to check out this ebook, Mars in 15 Minutes, the No Telescope Observation Guide. This comprehensive guide shows you exactly how to spot and track Mars with just your eyes, understand its movement through our sky, and connect with the red planet in ways you never imagined possible. It's perfect whether you're a complete beginner or someone who wants to deepen their cosmic connection. You'll find the link in the description below. But let's get back to the moon's deadly embrace. We need to talk about radiation, because this is where things become truly apocalyptic. Earth is protected by something extraordinary, a magnetic field generated by our planet's molten iron core. This invisible shield deflects most of the charged particles streaming from the sun. We also have a thick atmosphere that absorbs gamma rays, X-rays, and other nasty forms of radiation. Together, these two protective layers create a cozy bubble where life can flourish. The moon has neither. No global magnetic field, no atmosphere worth mentioning. It's completely exposed to the full fury of space radiation. There are two primary threats: galactic cosmic rays and solar particle events. Galactic cosmic rays are atomic nuclei, mostly protons and helium nuclei, accelerated to nearly the speed of light by supernova explosions and other violent cosmic events. They zip through space, carrying enormous amounts of energy. When they slam into human tissue, they don't just damage cells, they obliterate molecular structures, shredding DNA and creating cascades of secondary particles that cause even more havoc. Solar particle events are equally terrifying but more unpredictable. Our sun, that beautiful glowing orb that makes life possible on Earth, occasionally throws cosmic tantrums. Massive eruptions called coronal mass ejections hurl billions of tons of plasma into space at speeds exceeding 1,000 kilometers per second. When these plasma clouds are aimed at the moon, any astronauts on the surface face a potentially lethal dose of radiation within hours or even minutes. Here's the truly frightening part. We can't predict these events with perfect accuracy. Solar physicists have made tremendous progress in understanding our star's behavior. Missions like the Solar Dynamics Observatory, launched in 2010, monitor the sun continuously. The Parker Solar Probe, humanity's first mission to touch the sun, has been collecting data from within the solar corona since 2018. Yet despite all this technology, we still can only forecast major solar storms with maybe 1 or 2 days of warning at best, sometimes just hours. Imagine you're on the lunar surface, exploring a crater or setting up scientific equipment, and mission control suddenly alerts you that a massive solar particle event is incoming. You have perhaps 6 hours to get to shelter, but you're kilometers away from your habitat. The terrain is treacherous, covered in regolith that's been pulverized over billions of years into a consistency somewhere between sand and flour. Your suit is heavy. Moving quickly is exhausting in 1/6 Earth's gravity, but not as easy as science fiction makes it look. Can you make it back in time? Even if you do reach your habitat, the question becomes, is it adequately shielded? The Apollo lunar module had aluminum walls about as thick as a few sheets of heavy paper. That's fine for short visits when solar activity is calm, but for long-duration stays you need serious shielding. The problem is that every kilogram of shielding material you bring from Earth costs thousands of dollars to launch. You're caught in a brutal trade-off between safety and economics. Current research published in 2026 explores innovative solutions. Scientists at institutions like the University of Michigan are investigating active magnetic shielding systems, essentially creating artificial magnetospheres around habitats. The concept is elegant. Generate a magnetic field strong enough to deflect charged particles before they reach human occupants. But the engineering challenges are immense. You need superconducting magnets operating continuously in an environment with extreme temperature fluctuations, no atmosphere for cooling, and constant exposure to abrasive dust. Plus, the energy requirements are substantial. Others propose using lunar regolith itself as shielding. If you could pile several meters of lunar soil on top of habitats, it would provide significant protection against both galactic cosmic rays and solar particle events. Some designs envision inflatable habitats that astronauts cover with regolith using robotic equipment. Others imagine excavating into crater walls or lava tubes, creating underground bases shielded by natural geology. These aren't bad ideas, but they require heavy construction equipment, sophisticated robotics, and years of preparation before humans can safely inhabit these spaces. Let's talk about what radiation actually does to the human body over extended periods, because the effects are cumulative and devastating. When high-energy particles tear through cells, they damage DNA. Your body has remarkable repair mechanisms, evolved over millions of years to fix occasional damage, but space radiation overwhelms these systems. Studies conducted on the International Space Station, which orbits within Earth's protective magnetic field at an altitude of about 400 kilometers, show that astronauts experience DNA damage rates far higher than people on Earth's surface. On the Moon, where radiation exposure is roughly 2 to 3 times higher than on the ISS, the damage accumulates faster. Cancer risk increases dramatically. Cardiovascular disease becomes more likely as radiation damages the endothelial cells lining blood vessels. But perhaps most disturbing are the effects on the central nervous system. Research on mice exposed to simulated cosmic ray radiation shows troubling changes: cognitive impairment, memory problems, anxiety-like behaviors, and structural changes in brain tissue. Imagine spending 2 years constructing a lunar base only to return to Earth with your memory compromised, your risk of cancer elevated by 30 or 40%, and your cardiovascular system aged by a decade. This isn't science fiction. These are projections based on current radiation exposure models developed by NASA's Human Research Program and published in peer-reviewed scientific journals. Now, combine the radiation threat with another silent killer: the psychological impact of isolation. The Moon is 384,400 kilometers from Earth. That might not sound far in cosmic terms, but it's far enough that communication delay becomes noticeable. Radio signals, traveling at the speed of light, take about 1.3 seconds to travel from Earth to the Moon. That means a 2.6-second delay in any conversation. It doesn't sound like much, but it's enough to make real-time dialogue feel awkward and disconnected. You're living in a cramped habitat with the same handful of people for months. Outside your small windows, you see an airless, grey, utterly lifeless landscape that never changes. No clouds roll by, no birds fly overhead, no trees sway in the breeze because there is no breeze. The sky is always black, even during the lunar day, because there's no atmosphere to scatter light. Earth hangs in the sky, slowly going through phases, a constant reminder of everything you left behind. Psychological studies of people in isolated, confined, extreme environments, from Antarctic research stations to submarine crews, consistently show the same patterns. After the initial excitement wears off, which usually takes a few weeks, people experience various forms of psychological strain. Sleep disturbances are common, partly because your circadian rhythm evolved over millions of years to sync with Earth's 24-hour day-night cycle, gets confused by the Moon's 29.5-day cycle. Interpersonal conflicts emerge, often over trivial issues that become magnified in close quarters. Depression and anxiety can develop even in psychologically robust individuals carefully selected and trained for the mission. The Apollo astronauts were never on the Moon for more than 3 days. That's basically a long camping trip. You can tolerate almost anything for 72 hours. But living there for months or years? That's a completely different challenge, one we're only beginning to understand. Current analog studies, where researchers simulate lunar conditions on Earth, provide valuable data. NASA's Hera facility, the Human Exploration Research Analog, confines small crews in a habitat for up to 45 days. Similar studies occur in places like the Mars Desert Research Station in Utah and the HICS habitat in Hawaii. These studies reveal important insights. Crew composition matters enormously. Teams need a mix of personalities, skills, and coping strategies. Communication protocols must be carefully designed. Privacy, even in small amounts, becomes psychologically crucial. Access to meaningful work that feels purposeful helps maintain mental health. But these are still simulations on Earth, where participants know they can leave in an emergency, where the environment outside isn't immediately lethal, where rescue is always possible. On the Moon, there's no calling off the mission if things get too difficult. There's no emergency evacuation unless a spacecraft happens to be available and conditions permit launch. You're committed, and that psychological weight, that knowledge that you're truly isolated in one of the most hostile environments imaginable, carries its own burden that's difficult to simulate or prepare for adequately. Let's shift gears and talk about something that might seem mundane, but is actually critically important: food and water. On Earth, we take these for granted. Turn on a faucet, water flows. Walk to a grocery store or open your refrigerator, food is there. But on the Moon, every single molecule of water and every calorie of nutrition must either be brought from Earth at enormous cost or produced locally through complex systems that can fail. Water is particularly tricky. The human body needs about 2 to 3 liters per day just for drinking. Add in hygiene, food preparation, and life support systems that use water for various functions, and you're looking at roughly 50 kilograms of water per person per week. For a crew of 4 over a 6-month mission, that's about 5,000 kilograms of water. Launching that much mass from Earth would cost millions of dollars. The discovery of water ice in permanently shadowed lunar craters was thrilling precisely because it offers an alternative. Missions like NASA's Lunar Reconnaissance Orbiter and the Elkaros Impact Experiment in 2009 confirmed that substantial water ice exists near the lunar poles. India's Chandrayaan-1 mission and the more recent Artemis program findings have refined our understanding of where this ice is located and how much exists. But here's the problem: extracting that water is incredibly difficult. These permanently shadowed regions are among the coldest places in the solar system, with temperatures dropping to -233 degrees Celsius. That's just 40 degrees above absolute zero. At these temperatures, equipment behaves in unpredictable ways. Metals become brittle, lubricants freeze solid, electric components can fail. You'd need specialized mining equipment capable of operating in total darkness in conditions colder than anywhere humans have ever worked. Even if you successfully extract ice, you then need to purify it. Lunar water ice isn't pure. It's mixed with regolith and possibly contains volatile compounds that have been accumulating for billions of years. Some of these compounds could be toxic. You'd need sophisticated filtration and purification systems, all of which must operate reliably with minimal maintenance in a dust-contaminated environment. Now let's talk about food. Bringing all food from Earth is possible for short missions, but becomes impractical for permanent settlement. A single person needs roughly 0.5 kilogram to 1 kilogram of food per day, depending on activity level and the food's water content. That's between 180 and 365 kilograms per person per year. For a small colony of even a dozen people, you're talking about several tons of food annually, and that's before accounting for inevitable spoilage and waste. The obvious solution is to grow food on the moon. Plants convert carbon dioxide into oxygen through photosynthesis while producing edible biomass. It sounds perfect, but lunar farming faces challenges that would break even the most dedicated gardener's spirit. First, there's no soil in the traditional sense. Lunar regolith lacks organic matter, beneficial microorganisms, and the complex chemistry that makes Earth's soil a living ecosystem. It's essentially crushed rock with some interesting minerals. Worse, lunar regolith contains compounds called perchlorates, which are toxic to most plants and harmful to humans if ingested in sufficient quantities. Before you could use lunar material for farming, you'd need to extensively process and treat it, adding organic matter, beneficial bacteria, and nutrients while removing toxic compounds. All of this requires resources, energy, and complex systems. Then there's the lighting problem. Plants need light, lots of it, in specific wavelengths. On Earth, sunlight is free and abundant. On the Moon, during the lunar day, sunlight is actually too intense, delivering unfiltered solar radiation that can damage plant tissues. During the lunar night, which lasts about 14 Earth days, there's no sunlight at all. You'd need massive arrays of grow lights powered by nuclear reactors or enormous solar panel installations with equally massive battery systems to store energy through the long night. Temperature control adds another layer of complexity. The lunar surface experiences temperature swings from about 127 degrees Celsius during the day to minus 173 degrees Celsius at night. Plants, being delicate living organisms, need stable temperatures within a narrow range, typically 15 to 30 degrees Celsius depending on species. Maintaining that stability requires substantial energy for heating and cooling. Water and atmosphere management in a greenhouse environment also presents challenges. Plants transpire, releasing water vapor that must be captured and recycled. They need carbon dioxide, which is actually available from human respiration, creating a nice synergy. But balancing all these factors in a closed-loop system where nothing can be wasted requires sophisticated environmental controls that must operate flawlessly for years. Despite these challenges, experiments are underway. China's Chang'e 4 mission successfully germinated cotton seeds on the far side of the Moon in 2019, although the plants died when lunar night arrived and temperatures plummeted. NASA and other space agencies are developing advanced plant growth systems designed specifically for extraterrestrial environments. The vegetable production system, called VEGI, has been operating on the International Space Station since 2014, providing valuable data on space agriculture. But here's a sobering reality that brings us back to the radiation problem. Plants are also damaged by cosmic rays and solar particle events. Studies show that radiation can cause mutations, reduce crop yields, and create unpredictable changes in plant biochemistry. You'd need to shield your greenhouses just like you shield habitats, adding mass and complexity to an already challenging system. Let's discuss something that might surprise you. The moon is seismically active. When most people picture the moon, they imagine a dead world, geologically frozen in time. But lunar seismometers placed by Apollo astronauts detected thousands of moonquakes during their operational period from 1969 to 1977. Some of these quakes originated deep within the moon's interior, possibly from tidal stresses caused by Earth's gravitational pull. Others were shallow quakes that, while relatively small by terrestrial standards, lasted far longer than earthquakes because the moon lacks water and atmosphere to dampen seismic waves. The Apollo 17 seismometer recorded one shallow moonquake that continued for more than an hour, something virtually unheard of on Earth, where quakes typically last seconds or minutes. For structures built on the lunar surface, this sustained shaking could pose serious problems. Habitats need to be engineered to withstand not just the initial shock, but prolonged vibration that could fatigue materials and compromise structural integrity. More concerning are the impacts. The moon's scarred face testifies to billions of years of meteorite bombardment. Without an atmosphere to burn up incoming objects, even small meteorites strike the surface at full cosmic velocity. During the Apollo missions, seismometers detected numerous meteorite impacts, some releasing energy equivalent to tons of TNT. A habitat or critical piece of infrastructure struck by even a relatively small meteorite could be catastrophically damaged. Statistical analysis suggests that a habitat on the lunar surface has a non-trivial probability of being struck by a meteorite capable of causing significant damage over a multi-decade operational lifetime. This means lunar architecture must incorporate redundancy, shielding, and rapid repair capabilities. You can't just build a simple dome and hope for the best. Every structure needs to be hardened against impacts, possibly buried under regolith, and designed with multiple compartments so that a breach in one section doesn't doom the entire facility. Now, let's explore something truly mind-bending about lunar time and human biology. Your body runs on circadian rhythms, biological clocks that regulate everything from sleep-wake cycles to hormone production to immune system function. These rhythms evolved to sync with Earth's 24-hour rotation period. Sunlight hitting your eyes in the morning triggers cascades of hormonal changes that make you alert. Darkness in the evening prompts melatonin production that makes you sleepy. The lunar day, called a lunation, lasts 29.5 Earth days. That means roughly 14.5 days of continuous sunlight, followed by 14.5 days of continuous darkness. Your circadian system has no idea what to do with that. Research on people subjected to prolonged light or dark periods shows consistent problems: disrupted sleep patterns, metabolic dysregulation, mood disturbances, and impaired cognitive function. Some have proposed that lunar colonists simply ignore the natural light-dark cycle and maintain artificial 24-hour schedules inside habitats with controlled lighting. That's certainly possible and probably necessary, but it creates an odd disconnect where the environment outside your windows bears no relationship to your daily routine. Over months and years, this cognitive dissonance, constantly living out of sync with your visible environment, could have subtle psychological effects we don't fully understand yet. There's also the question of human reproduction, though this ventures into territory where we have almost no data. If we're talking about permanent colonization, eventually we need to consider whether humans can successfully reproduce and develop in lunar gravity. 1/6 Earth gravity is enough to keep you grounded, but is it enough for proper fetal development, for bone and muscle growth in children, for cardiovascular system maturation? Studies on animals exposed to microgravity or reduced gravity provide some clues, mostly concerning ones. Bone density decreases without adequate gravitational loading, muscles atrophy, the cardiovascular system, not having to work as hard to pump blood against gravity, becomes deconditioned. While adults can counteract some of these effects through rigorous exercise, a developing fetus has no such option. The mechanical forces that help shape developing bones, organs, and tissues would be fundamentally different in lunar gravity. No human has ever been conceived, gestated, or born anywhere but Earth. The idea of lunar pregnancy and childbirth raises medical questions that would require extensive animal studies before anyone could ethically attempt it. And even then, what kind of childhood would a lunar-born child experience? Would they ever be able to visit Earth, where their body, adapted to 1/6 gravity, would suddenly weigh 6 times as much? Could their bones and muscles handle that transition? These questions might seem distant, relevant only for some far future scenario. But if we're seriously talking about colonization rather than just temporary outposts, these biological realities become central concerns. A colony that can't sustain itself across generations isn't truly colonizing, it's just camping with better equipment. Let's shift to infrastructure and ask a practical question. How do you build anything on the Moon? Every construction project on Earth relies on certain assumptions. You have atmosphere, so you can use compressed air tools. You have gravity, enough to make cranes and hoists work predictably. You have abundant materials, from concrete to steel to lumber. You have a workforce that can work outside for extended periods wearing minimal protective equipment. None of that applies on the Moon. Construction workers would need to wear bulky spacesuits that limit dexterity and vision. The suits must be meticulously maintained because a single puncture could be fatal. Working in direct sunlight means surface temperatures hot enough to boil water, while areas in shadow are cold enough to freeze carbon dioxide. Tools and equipment must be specially designed to operate in vacuum conditions, where there's no air for cooling, where lubricants evaporate, and where thermal expansion and contraction are extreme. Traditional construction materials don't work well either. Concrete requires water, which is precious. Steel is enormously expensive to transport from Earth. Wood doesn't exist. Instead, researchers are exploring techniques like sintering lunar regolith, using concentrated sunlight or microwave energy to fuse particles into solid structures. Others investigate three-dimensional printing with regolith-based materials, building habitats layer by layer using robotic systems. These technologies show promise in laboratory settings, but we haven't yet demonstrated them at scale in actual lunar conditions. There's a huge difference between printing a small test structure in a lab and constructing a habitat that must maintain perfect pressure integrity, provide radiation shielding, and remain habitable for years in the hostile lunar environment. Power generation presents its own set of challenges. Solar power seems like an obvious choice since the Moon receives abundant sunlight, unfiltered by atmosphere, for 14.5 days at a time, but then comes 14.5 days of darkness. Battery technology has improved dramatically, but storing enough energy to run life support systems, environmental controls, research equipment, and other necessities for 2 weeks of continuous operation requires massive battery banks. The lunar poles offer a partial solution. Certain locations near the poles experience near-constant sunlight due to the Moon's orbital geometry. Peaks on crater rims catch sunlight for around 80 to 90% of each lunar day-night cycle. This is one reason NASA's Artemis program targets the South Polar region for initial exploration and potential base construction. But even these peak locations have brief periods of darkness, and they're often located in rugged terrain that complicates construction and operations. Nuclear power provides an alternative. Small nuclear reactors could provide steady, reliable power regardless of day-night cycles. NASA has developed concepts like the Killer Power System, a small fission reactor designed specifically for space applications. A 10-kilowatt kilopower unit, about the size of a trash can, could provide continuous electricity for years with minimal maintenance. Scale that up to 40 or 100 kilowatts, and you have enough power for a small lunar base. But nuclear systems carry their own concerns. There's the political and public relations challenge of launching nuclear material from Earth. There's the engineering challenge of ensuring the reactor can operate safely in lunar conditions with adequate cooling, which is surprisingly difficult in vacuum, where heat can only be radiated away, not conducted or convected. And there's the question of what happens if something goes wrong. A reactor malfunction on Earth can be managed by evacuation and containment. On the Moon, where the base depends on that reactor for survival, the stakes are infinitely higher. Communication infrastructure is another often overlooked challenge. Earth-Moon communication is relatively straightforward when the base is on the lunar near side, the hemisphere always facing Earth. You need line of sight to Earth for radio communication, and the near side provides that. But if you want to explore or build on the far side, which never faces Earth, you need relay satellites. China demonstrated this with the Queqiao satellite, positioned at the Earth-Moon Lagrange point to relay communications for their Change 4 far-side lander. For a permanent lunar presence, you'd need a robust network of communication satellites, providing continuous coverage of the entire lunar surface. These satellites must be maintained, occasionally replaced, and kept operational despite radiation exposure and micrometeorite impacts. It's another layer of infrastructure that must function perfectly, because losing communication could mean losing contact with isolated exploration teams or remote facilities during emergencies. Medical care on the Moon represents perhaps one of the most sobering challenges. On Earth, if you have a medical emergency, you can usually reach advanced care within hours. Helicopter evacuations, ambulances, emergency rooms staffed with specialists and equipped with diagnostic tools and treatment options. On the Moon, the nearest advanced medical facility is 384,400 kilometers away, a journey requiring days even with the fastest currently conceivable spacecraft. What happens if someone suffers a serious injury, a construction accident that causes internal bleeding, a burst appendix, a heart attack, a severe reaction to medication or contamination? Lunar bases would need medical facilities capable of handling not just minor injuries, but potentially life-threatening emergencies. That means surgical capability, diagnostic imaging equipment, laboratory facilities for blood work and testing, and personnel trained in emergency medicine. But here's the problem. Medical equipment designed for Earth often doesn't work in reduced gravity or vacuum conditions. Intravenous fluids behave differently. Blood pressure measurements require recalibration. Surgical procedures that rely on gravity for blood drainage or organ positioning become complicated. Sterilization protocols must be adapted to environments where you can't simply open a window for ventilation. Medications have finite shelf lives. Even with careful storage, pharmaceuticals degrade over time. A lunar base would need a constantly refreshed pharmacy, with regular resupply missions bringing fresh medications. But what if a critical drug is needed and isn't available? What if someone develops an allergy or adverse reaction to the only available treatment option? There's also the challenge of diagnostic uncertainty. Telemedicine helps, allowing Earth-based specialists to consult via video link despite the communication delay. But many diagnoses require physical examination, lab tests, and imaging that might not be available on site. A doctor on the Moon might face agonizing decisions with incomplete information and limited resources. Knowing that evacuation to Earth isn't immediately possible, mental health care becomes equally critical. We've already discussed the psychological stresses of lunar life. Having trained psychologists or psychiatrists available, either in person or via telemedicine, isn't optional, it's essential. But treating serious mental health crises, particularly if someone becomes a danger to themselves or others in the confined environment of a lunar habitat, presents challenges without good precedents or easy solutions. Let's talk about something that sounds almost trivial but isn't: dust. Lunar regolith isn't like beach sand or garden soil. Billions of years of meteorite impacts have pulverized the surface into particles that are incredibly fine, jagged, and abrasive. Without wind or water to smooth them, these particles retain sharp edges that make them cling to everything through electrostatic forces. Apollo astronauts reported that lunar dust infiltrated every seal, scratched visors and equipment, and couldn't be fully cleaned off. Harrison Schmitt, the geologist who walked on the moon during Apollo 17, experienced what he called lunar hay fever, a reaction to dust particles that made it into the lunar module. Despite careful cleaning procedures, he experienced respiratory irritation and eye discomfort. Now imagine living with this for months or years. The dust doesn't just coat surfaces, it's potentially toxic. Studies of lunar samples show that the sharp particles can damage lung tissue if inhaled. They contain compounds that might trigger inflammatory responses or worse. Every time an airlock cycles, bringing astronauts in from outside, dust comes with them. Designing airlocks with multiple stages, including vacuum chambers where dust can be blown off before entering living spaces, helps but doesn't eliminate the problem entirely. Over time, dust accumulates in habitats. It gets into air filters, requiring frequent replacement. It contaminates food preparation areas. It infiltrates mechanical systems, causing wear and potentially failures. Some research suggests using electron beams or other technologies to neutralize the electrostatic charge that makes dust cling so stubbornly, but these systems add complexity and potential failure points. Others propose designing spacesuits that remain permanently outside, with astronauts climbing into them through rear hatches, so the contaminated exterior never enters living spaces. These are clever solutions, but they require extensive testing and development before they can be trusted with human lives. Transportation on the lunar surface presents interesting challenges. The Apollo lunar roving vehicle, used on the final 3 Apollo missions, could travel at a maximum speed of about 18 kilometers per hour and had a range of roughly 92 kilometers from the lunar module, limited by life support consumables and the requirement that astronauts be able to walk back if the rover failed. For exploring small areas over short missions, this worked fine. But for a permanent base conducting extensive exploration and resource extraction, you need more capable vehicles. Pressurized rovers that astronauts can live in for days or weeks, essentially mobile habitats, would enable long-distance exploration. These vehicles would need to carry life support systems, scientific equipment, supplies, and provide protection from radiation and meteorite impacts. They'd need reliable power systems, probably a combination of solar panels and batteries, or perhaps radioisotope power sources for operations during lunar night. The terrain is treacherous. The moon's surface is covered with craters ranging from microscopic to hundreds of kilometers across, large boulders scattered across plains, steep slopes inside craters, deep crevasses where the crust has cracked. Navigation requires detailed mapping and careful route planning. Even then, unexpected obstacles could strand vehicles far from base. Rescue missions in such scenarios would be complex operations requiring multiple vehicles and personnel, all while managing life support consumables and radiation exposure. Let's consider the legal and political dimensions. because they're deeply intertwined with the practical challenges. The Outer Space Treaty of 1967, signed by over 100 nations including all major spacefaring powers, establishes that celestial bodies cannot be claimed by any nation through sovereignty. Outer space, including the Moon, is the province of all humankind. Sounds idealistic and wonderful, right? But it creates ambiguity. If no nation can claim lunar territory, what happens when multiple countries or private companies want to establish bases in the same region, perhaps competing for access to water ice deposits in a particularly favorable polar crater? Who has priority? Who mediates disputes? The treaty prohibits national appropriation but doesn't clearly address resource extraction rights or property claims for facilities constructed on the lunar surface. The Artemis Accords, introduced by NASA in 2020 and signed by multiple partner nations, attempt to establish principles for lunar exploration, including safety zones around landing sites and facilities. But not every spacefaring nation has signed them. China and Russia, both pursuing their own lunar ambitions, have not joined the accords. This raises the possibility of competing frameworks for lunar governance and potential conflicts over resource access and operational territory. Private companies add another layer of complexity. SpaceX, Blue Origin, and other commercial entities are developing capabilities to reach the Moon. If a private company establishes a lunar mining operation, who regulates it? Who ensures environmental protection, if such a concept even applies to an already dead world? Who prevents monopolistic control over critical resources like water ice deposits? These aren't just abstract legal questions. They have practical implications for anyone living on the Moon. Imagine you're part of a lunar base operated by one nation or company, and a competing base from another entity sets up operations nearby, perhaps close enough that their activities affect your access to resources or create safety concerns. Without clear international governance mechanisms, how are such conflicts resolved? There's also the question of who bears responsibility when things go wrong. If an accident at one nation's lunar facility causes contamination or damage that affects another nation's base, what recourse exists? If a private company goes bankrupt and abandons lunar infrastructure that becomes a hazard to navigation or operations, who cleans it up? Economic viability is perhaps the ultimate question that determines whether lunar colonization happens at all. Governments can fund exploration missions motivated by science, prestige, and strategic interests. But long-term colonization requires economic justification, especially if private investment plays a significant role. The Moon needs to offer something valuable enough to justify the enormous costs of getting there and staying there. Several possibilities have been proposed. Lunar water could be processed into hydrogen and oxygen for rocket fuel, potentially establishing the Moon as a refueling station for missions to Mars and beyond. This makes economic sense because launching fuel from the Moon's weaker gravity well is far cheaper than lifting it from Earth. But this only works if there's sufficient demand for deep space missions to justify the infrastructure investment. Helium-3, a rare isotope on Earth but relatively abundant in lunar regolith, has been proposed as fuel for future fusion reactors. The idea is tantalizing: mine helium-3 on the Moon, ship it to Earth, and power civilization with clean fusion energy. The problems are that we don't yet have working fusion reactors that can use helium-3. The mining operation would need to process hundreds of thousands of tons of regolith to extract meaningful quantities, and the entire business model depends on fusion technology that remains frustratingly out of reach, despite decades of research. Tourism is another possibility. Just as wealthy individuals now pay for trips to the International Space Station, perhaps lunar tourism could become a luxury industry. Experience 1/6 gravity, gaze at Earth hanging in the black sky. explore historic Apollo landing sites. There's certainly appeal, but the costs would be astronomical, probably millions of dollars per person for the foreseeable future, limiting the market to an extremely small demographic. And tourist facilities would require all the same infrastructure we've been discussing: life support, radiation protection, medical care, plus additional amenities expected by paying customers. Scientific research has inherent value but typically doesn't generate direct economic returns. The Moon offers unique opportunities for astronomy, particularly radio astronomy on the far side where Earth's radio noise is completely blocked. The geology of an ancient, largely unchanged surface tells stories about the early solar system. Studying how organisms adapt to lunar conditions advances biology. But science usually requires sustained public funding rather than generating profits that could sustain a colony economically. Manufacturing is perhaps the most interesting long-term possibility. The Moon's vacuum environment, low gravity, and access to solar energy and raw materials could enable manufacturing processes difficult or impossible on Earth. Growing ultra-pure crystals for semiconductors, creating specialized alloys in vacuum conditions, constructing large space structures where the low gravity makes handling massive components easier. But all of this requires substantial upfront infrastructure investment before any return is realized. The harsh reality is that there's no clear economic driver for lunar colonization comparable to historical drivers of terrestrial colonization: accessible land, exploitable resources, trade routes, or favorable climates. The Moon is fundamentally hostile, expensive to reach, and doesn't offer anything you can't eventually obtain elsewhere with less difficulty, at least not with current or near-term technology. This doesn't mean colonization won't happen, but it means the path forward will likely be gradual, driven initially by government investment in exploration and science, slowly building infrastructure that eventually might enable commercial activities. It's a decades-long process, possibly century-long, rather than something that happens in a single generation. Now let's discuss fire safety, which is both critically important and surprisingly complex in a lunar environment. On Earth, fire requires fuel, oxygen, and heat. In a lunar habitat, you have all three. Oxygen is abundant because you're maintaining a breathable atmosphere. Electrical equipment, plastics, fabrics, and other materials provide fuel. And you have heat sources everywhere: electronics, power systems, heating elements. But fire behaves differently in reduced gravity and enclosed environments. Flames on Earth are shaped by buoyancy, hot gases rising and drawing in fresh oxygen from below. In lunar gravity, this convection is much weaker. Flames tend to be more spherical, spreading in all directions rather than primarily upward. They can smolder and spread in unexpected patterns. Smoke doesn't rise predictably, making detection and evacuation more complicated. A fire in a habitat could be catastrophic. You can't just open doors and windows to vent smoke because outside is vacuum. The fire consumes your precious oxygen while producing toxic gases like carbon monoxide and carbon dioxide. Extinguishing it requires systems that work in reduced gravity and in enclosed spaces where suppressants must be carefully chosen so they don't create secondary hazards or deplete breathable atmosphere. Water-based suppression systems add weight and complexity. Carbon dioxide systems can suffocate occupants if not managed carefully. Halon and similar chemicals effective for fire suppression have environmental and health concerns. Every habitat needs fire detection, suppression systems, compartmentalization to contain fires, and well-practiced evacuation procedures. But where do you evacuate to? Another module, assuming fire doors seal properly, emergency shelters, spacesuits in the airlock, hoping to survive outside until rescue arrives. The psychological impact of a fire in an isolated lunar habitat, where there's literally nowhere to run, would be terrifying even if successfully controlled. The knowledge that fire is an ever-present risk that could destroy your only protection against vacuum and radiation adds yet another layer of stress to daily life. Let's talk about something more mundane but no less important: waste management. Every human produces waste, biological and otherwise. On Earth, we have elaborate systems for handling this: sewage treatment plants, landfills, recycling facilities, composting operations. On the Moon, you need to handle waste with near-perfect efficiency because everything is a resource you can't afford to lose. Human waste contains water, which must be recaptured. It contains organic compounds that can be broken down and reprocessed. Even the solid components can potentially be used, perhaps as biomass for agricultural systems after appropriate treatment. The International Space Station uses systems that recycle urine into drinkable water through multi-step filtration and purification. Similar systems would be essential on the Moon, though the psychological barrier of drinking recycled urine remains significant for many people despite the water being chemically pure. Solid waste management is trickier. Feces contain pathogens that must be neutralized. Various approaches exist: incineration, which requires energy and produces gases that must be managed; composting, which takes time and space; or chemical treatment to break down organic matter. All of these must operate reliably in lunar gravity and without creating hazards or unpleasant conditions in the confined habitat. Biological waste poses different challenges: packaging materials, broken equipment, worn-out spacesuits, failed electronics. All of this accumulates. On Earth, you throw things away and they disappear into waste streams. On the Moon, there is no away. Every piece of waste either needs to be recycled, repurposed, stored indefinitely, or perhaps eventually launched into space or dumped in permanently shadowed craters far from inhabited areas. Recycling is essential but energy-intensive. Melting down metals to recast them into new components requires furnaces and manufacturing equipment. Breaking down plastics and reforming them into useful materials requires chemical processes. Some materials might be impossible to recycle with available technology, forcing you to either stockpile them or find creative ways to repurpose them. Perhaps broken ceramic components become aggregate for regolith-based concrete. Perhaps shredded fabric becomes insulation material. The challenge is that recycling infrastructure is heavy, complex, and requires skilled operators. Early lunar bases probably won't have comprehensive recycling capability, meaning waste accumulates and must be stored, with the hope that future missions can bring recycling equipment. But storage space is limited, and waste is depressingly efficient at filling available volume. There's also hazardous waste. Spent batteries containing toxic materials, cleaning solvents, medical waste potentially contaminated with pathogens, radioactive materials if nuclear power systems are used. Each category requires specific handling protocols. Mix the wrong things together and you risk fires, toxic releases, or contamination. Proper waste segregation, labeling, and storage become critical safety practices that everyone must follow meticulously. Let's shift to thinking about education and skill requirements. A lunar colony can't afford passengers. Every person needs to contribute productively, and ideally, everyone should have multiple capabilities. You need people with engineering skills to maintain life support systems, habitat structures, and power generation. You need medical personnel. You need scientists conducting the research that justifies the base's existence. You need specialists in agriculture if you're growing food. You need communications experts managing Earthlinks and satellite networks, but you also need people who can perform manual labor, repair things, troubleshoot unexpected problems, and adapt to novel situations. The most valuable colonists would be those with diverse skill sets: an engineer who's also trained in emergency medicine, a biologist who understands electrical systems, a geologist who can operate heavy equipment and perform equipment maintenance. Training for lunar missions would be extraordinarily intensive, likely taking years. You need to master your primary specialization, develop secondary skills, train for emergency scenarios, learn to operate in spacesuits and reduced gravity, study lunar geology and environment, understand radiation safety, and develop the psychological resilience to handle isolation and stress. Not everyone has the aptitude, and even among those who do, the training commitment eliminates many potential candidates who have other life priorities. This creates a demographic challenge. Lunar colonists would be highly selected individuals, skewing towards certain personality types, educational backgrounds, and age ranges. They probably wouldn't represent a cross-section of humanity. They'd be disproportionately STEM educated, physically fit, psychologically screened for stress tolerance, and willing to accept enormous personal sacrifice. Over time, this creates a unique subculture that might become increasingly distant from Earth-based society in values, perspectives, and priorities. Children complicate this further. If we're talking about true colonization rather than just long-term missions, eventually children would be born on the moon or brought there at young ages. Their education would need to cover not just standard academic subjects, but also survival skills specific to the lunar environment. Growing up in 1/6 gravity in confined spaces, never experiencing rain or wind or open skies, never seeing wild animals or natural forests, how does this shape psychological and cognitive development? Would lunar-born children feel any connection to Earth? Would they consider themselves human in the same way Earth-born people do, or would they develop a distinct identity as Lunarians or something similar? Would they resent being born into an environment they didn't choose, where leaving to experience Earth might be medically impossible due to physiological adaptations to low gravity? These questions venture into speculative sociology, but they're relevant for understanding what colonization truly means. A colony that depends on continuous influx of Earth-born specialists isn't self-sustaining. A truly independent lunar civilization would need to reproduce, raise children to adulthood, and educate them to maintain and advance the colony's infrastructure and knowledge base. That's an enormously more complex challenge than simply keeping a rotation of specialists alive and productive. Social structure and governance become fascinating questions. Early lunar bases would likely operate under hierarchical command structures similar to military units or Antarctic research stations. There's a commander or base director who makes final decisions with clear chains of authority for different operational areas. This makes sense when you have small populations of highly trained specialists where coordination and quick decision-making are essential for survival. But as populations grow, hierarchical structures can become stifling. People want input into decisions that affect their lives. They want some degree of autonomy and self-determination. How does a lunar colony transition from authoritarian efficiency to more democratic governance without compromising the discipline and coordination necessary for survival? Do lunar colonists remain citizens of their Earth nations, subject to Earth laws and governance? Do they develop their own legal systems adapted to lunar circumstances? If someone commits a crime on the moon, who has jurisdiction? What happens if there's a dispute between colonists from different nations operating under different legal frameworks? Imagine a scenario. A technician from one nation's base commits assault against a scientist from another nation's base during a joint expedition. Which nation's laws apply? Who conducts the investigation? Who administers punishment? Can you imprison someone on the moon, dedicating precious life support resources to maintain a prisoner? Do you send them back to Earth for trial and incarceration, and who pays for that? Or do lunar communities develop their own justice systems, perhaps emphasizing restorative rather than punitive approaches, because maintaining social cohesion is too critical to allow prolonged conflicts? These aren't trivial questions. Human societies have always struggled with justice, governance, and social order. Transplanting humans to an environment where survival depends on cooperation and functional technology adds urgent pressure to get these things right. A social breakdown in a lunar colony could be fatal not just for individuals, but for the entire community. Let's talk about something that might seem insignificant but isn't: personal space and privacy. Spacecraft and early lunar habitats will be cramped. Space is expensive. Every cubic meter requires structure, life support, and protection from radiation and vacuum. Efficiency demands minimizing volume, which means personal quarters will be small, probably smaller than a college dormitory room, possibly just sleeping pods with barely enough room to lie down and store a few personal items. Common areas would be shared: dining facilities, workspaces, exercise areas, bathrooms. You'd see the same small group of people every single day with no escape. Your private conversations might be overheard. Your personal habits, hygiene practices, eating patterns, everything becomes visible to your companions. For people accustomed to privacy, personal vehicles, the ability to go for a solitary walk or escape to a different environment when stressed, this constant proximity could be suffocating. Research on isolation facilities, submarines, and Antarctic stations shows that interpersonal conflicts often arise from seemingly trivial irritations amplified by constant proximity. Someone chews loudly, another person talks too much. Someone doesn't clean up properly after themselves. Normally, minor annoyances become major grievances when you can't escape them. Personality conflicts that could be managed on Earth through simple avoidance become ongoing sources of stress when you're trapped together. Habitat design can help somewhat. Providing small private spaces, even if they're just soundproofed sleeping pods, gives people somewhere to retreat. Creating common areas with different purposes: a quiet reading area, a social area for conversation, a workspace, allows people to self-segregate based on mood and needs. But there's only so much you can do within the constraints of limited volume and mass budgets. This is one reason why crew selection emphasizes psychological compatibility and stress tolerance. You're not just choosing qualified specialists, you're assembling a group of people who can live together harmoniously under extraordinarily difficult conditions. Psychological screening tries to identify people who are naturally even-tempered, conflict-averse, able to communicate effectively, and capable of finding contentment in limited environments, but no screening is perfect. People change under stress, relationships evolve. Someone who seemed perfectly compatible during training might reveal difficult traits after months in confinement. Having trained psychologists available, either on-site or via regular telemedicine sessions, becomes essential for managing interpersonal dynamics before they escalate into serious conflicts. Recreation and leisure also become crucial for mental health. On Earth, people decompress through enormous variety: sports, hobbies, entertainment, social activities, exploring new places, experiencing nature. On the Moon, options are severely limited. You can't go for a hike without donning a spacesuit and coordinating with safety protocols. There are no restaurants, no movie theaters, no concerts, no sports leagues. What you have is what you bring or create. Digital entertainment helps: movies, music, books, video games, virtual reality experiences. Communication with Earth allows video calls with family and friends, though the time delay makes real-time conversation impossible. Some physical activities are possible: exercise equipment, perhaps adapted versions of games that work in reduced gravity. Creative pursuits like art, music, writing, or crafts might be encouraged. Some habitats might include gardens or green spaces, not just for food production, but for psychological benefit. Humans have deep connections to living things and natural environments. Having plants to tend, green spaces to relax in, even just the sight and smell of growing things can significantly improve mental well-being. But again, this requires resources, space, water, lighting, nutrients, maintenance time. The danger is that without adequate recreation and mental stimulation, people deteriorate psychologically. Depression, anxiety, cognitive decline, interpersonal conflicts all become more likely. A lunar colony must budget not just for survival needs, but for quality of life elements that keep people psychologically healthy and productive. Let's discuss something that connects directly to the challenges we've been exploring: the parallels with Mars colonization. If you're fascinated by the challenges of living on the Moon, the prospects for Mars colonization present an even more complex puzzle. Mars is dramatically farther away, with communication delays of up to 22 minutes each direction, making real-time assistance from Earth impossible. The environmental challenges are different but equally daunting: a thin carbon dioxide atmosphere, massive dust storms, even lower gravity than the Moon at 38% of Earth's. We are exploring the Moon's brutal reality from a colonization perspective. But here's something you can do tonight. Actually see Mars with your own eyes. No telescope needed, no expensive equipment, just you and the night sky. Make sure to check out the ebook Mars in 15 Minutes, the No Telescope Guide. It shows you exactly how to spot Mars, when to look, what you're actually seeing, and how to track it across the sky, all without spending a cent on gear. In 15 minutes, you'll know more about observing Mars than most amateur astronomers. Links in the description. Go see the red planet for yourself tonight. Returning to the Moon, let's examine the challenge of expansion. Suppose the first lunar base succeeds. It keeps people alive, conducts valuable research, perhaps even achieves some economic productivity. What happens next? How does a single small outpost grow into multiple bases, then settlements, then eventually something resembling a true colony? Expansion requires either sending more people and equipment from Earth, or developing the capability to manufacture what you need from lunar resources. The former is expensive and slow, limited by launch capacity and budgets. The latter requires significant technological development and infrastructure investment before it starts paying returns. In situ resource utilization, or ISRU, is the term for using local materials rather than importing everything from Earth. We've already discussed extracting oxygen from regolith and mining water ice. But what about manufacturing structural materials, creating metal components from lunar ores, producing glass, ceramics, and concrete-like materials from processed regolith? All of this is theoretically possible. Lunar regolith contains silicon, aluminum, iron, calcium, magnesium, and other useful elements. With appropriate processing equipment, smelters, chemical reactors, manufacturing facilities, you can theoretically produce most of what you need for construction and expansion. But theoretically possible and practically achievable with current technology and reasonable resources are very different things. Consider a simple example: creating metal beams for structural support. On Earth, this involves mining ore, transporting it to processing facilities, smelting it in furnaces, casting or forging it into desired shapes, then transporting finished products to construction sites. The entire industrial infrastructure supporting this is staggeringly complex, built up over centuries of technological development. On the Moon, you'd need to recreate substantial portions of this industrial chain with equipment that can operate in vacuum, extreme temperatures, and abrasive dust conditions. You need power sources for energy-intensive processes like smelting. You need mining equipment to extract appropriate ores. You need processing facilities to refine them. You need manufacturing equipment to shape them into useful components. And you need skilled workers who can operate and maintain all of this equipment while also managing the 1,000 other tasks necessary for survival. The initial investment required to establish ISRU capability is enormous. You're essentially bootstrapping an industrial revolution on a dead world, sending the minimum necessary equipment from Earth to begin producing things locally, then gradually expanding capability with each successive production cycle. It's a decades-long process, even under optimistic assumptions. This creates a chicken and egg problem. You can't justify expanding the colony until you have ISRU capability, making expansion economically feasible. But you can't develop ISRU capability without sufficient people and infrastructure to build and operate the necessary facilities. Breaking out of this loop requires sustained commitment and investment over extended periods without guaranteed returns. Some proposals suggest robotic systems could establish initial ISRU infrastructure before humans arrive, similar to how we might send robots to Mars ahead of crewed missions. Autonomous systems could begin extracting resources, producing oxygen and water, even manufacturing structural components or habitat modules from lunar materials. By the time humans arrive, much of the basic infrastructure is already in place. This approach has appeal but faces significant challenges. Robotics technology, while advancing rapidly, still struggles with unstructured environments and unexpected problems. A robot that encounters a situation not anticipated by its programmers might fail or make poor decisions. Remote operation from Earth helps but suffers from the communication delay and requires constant human oversight. Fully autonomous systems capable of complex industrial processes in the lunar environment remain substantially beyond our current capabilities. More likely, lunar development will involve hybrid approaches, robots handling dangerous or repetitive tasks under human supervision, with human specialists available to troubleshoot problems, perform maintenance, and make decisions about adapting processes to actual conditions encountered. Transportation infrastructure becomes increasingly important as colonies expand. Early bases might be single locations, but eventually you'd want multiple sites, one near water ice deposits at the poles, another in equatorial regions for easier launch access, perhaps research stations at scientifically interesting locations like lava tubes or ancient volcanic sites. Moving between these sites requires transportation systems. Rovers can handle short distances, but longer trips demand more capable vehicles, pressurized rovers that serve as mobile habitats, allowing multi-day journeys without spacesuits. These would need reliable power systems, navigation equipment, life support, communication systems, and enough redundancy that a breakdown doesn't become a death sentence for the crew. Eventually, you might develop infrastructure analogous to roads or railways, cleared paths, charging stations, emergency shelters positioned at intervals, perhaps even tracks or guide systems for automated vehicles. But every piece of infrastructure requires resources to build and maintain, and early colonies operate under severe resource constraints. Some have proposed mass driver systems, electromagnetic catapults that could launch cargo from the moon's surface without rockets, taking advantage of the low gravity and lack of atmosphere. These could facilitate trade between lunar sites, launch resources to orbital facilities, or even send materials to Mars missions. But building a mass driver requires substantial infrastructure investment and only makes sense once you have significant quantities of material to move. The vision of lunar colonization often includes the idea of economic independence, colonies that produce enough value to sustain themselves without continuous subsidy from Earth. This is the ultimate test of whether colonization succeeds or remains a prolonged exploration program dependent on external support. Achieving economic independence requires finding things the Moon can produce that Earth wants and will pay for. We've discussed possibilities, fuel for deep space missions, rare materials, scientific data, perhaps manufactured goods that benefit from lunar conditions. But in every case, the economics are challenging. The Moon must produce things valuable enough that transporting them to customers justifies the cost, or attract customers willing to come to the Moon to obtain them. Tourism might seem like the easiest path to profitability, but the infrastructure required for tourism exceeds what's needed for specialist operations. Tourists expect safety, comfort, interesting activities, and reasonable costs. Delivering all of this while making a profit requires technological advances that reduce launch costs by orders of magnitude and establish lunar infrastructure far more extensive than anything currently envisioned. Perhaps the most realistic path to economic viability involves the Moon serving as infrastructure for further space development. If humanity seriously pursues Mars colonization, asteroid mining, or construction of large space habitats, the Moon could serve as a staging area, manufacturing center, and fuel depot. Materials launched from the Moon's weak gravity well could support construction projects in space far more economically than lifting everything from Earth. This creates a positive feedback loop. Space development activities create demand for lunar resources and services, funding lunar expansion, which increases capability to support further space development. But this only works if there's sufficient activity in cislunar space and beyond to create meaningful demand, something that remains speculative rather than certain. Let's address the fundamental question that underlies all of this. Should we colonize the Moon? We've spent considerable time discussing challenges and obstacles, but what about the deeper question of whether this is something humanity ought to pursue even if we can? Arguments in favor often emphasize survival and expansion. Earth faces existential risks, asteroid impacts, climate change, nuclear war, pandemics, supervolcano eruptions. Having human populations established off-world creates redundancy. If catastrophe devastates Earth, humanity survives elsewhere. The Moon, being close and relatively accessible, represents a logical first step toward becoming a multi-world species. There's also the argument from human nature and history. Exploration and expansion are deeply embedded in human behavior. Throughout history, humans have pushed into new frontiers, and those who did often drove technological innovation and cultural development. Space represents the ultimate frontier, and the Moon is the nearest destination where permanent presence is plausible with foreseeable technology. Scientific advancement provides another justification. The Moon offers unique research opportunities in astronomy, geology, physics, and biology. Understanding how life adapts to lunar conditions, or whether life ever existed in the early solar system, or observing the universe from the far side's radio-quiet environment. All of this expands human knowledge in ways that benefit everyone. But there are counter-arguments. The resources required for lunar colonization are staggering, potentially trillions of dollars over decades. Those resources could address urgent problems on Earth: poverty, disease, climate change, education, infrastructure. Is establishing a lunar colony more important than solving malaria, providing clean water to billions, or transitioning to sustainable energy systems? There's also the question of whether humans should be the ones going. Robotic systems are becoming increasingly capable and don't require life support, radiation shielding, or return trips. Perhaps scientific and economic goals can be achieved more efficiently through robotic missions, reserving human presence for situations where it provides clear advantages worth the additional cost and risk. Some argue that the drive to colonize other worlds reflects a dangerous mindset, that if we mess up Earth, we can just move somewhere else. This could reduce urgency around solving terrestrial problems. Why worry about environmental degradation when we can imagine escaping to space? Of course, this is partly a strawman argument, as anyone who understands the actual difficulty of space colonization recognizes that no extraterrestrial environment will ever be as hospitable as even a severely damaged Earth. There are also ethical considerations about contamination and planetary protection. Should we introduce Earth life to pristine environments? What if microbial life exists in lunar ice deposits, preserved from ancient cometary impacts? Would colonization destroy evidence before we discover it? Do celestial bodies have inherent value that we should preserve, or are they simply resources for human use? These philosophical and ethical questions don't have clear answers. Different people with different values will reach different conclusions. What's important is that these discussions happen thoughtfully, considering both possibilities and consequences, rather than proceeding based on unreflective assumptions about human destiny or technological inevitability. So, where does all of this leave us? Lunar colonization is possible in principle. We have the basic understanding of physics, engineering, and biology needed to keep humans alive on the moon for extended periods. But possibility doesn't equal practicality, and practicality doesn't equal inevitability. The path from current capabilities to genuine lunar colonies involves solving interconnected technical, economic, political, and social challenges. Every system we've discussed, life support, radiation protection, power generation, food production, construction, transportation, governance, economics, must work reliably together. Failure in any one system can cascade into broader failure. Success requires sustained commitment over decades, probably from multiple nations and organizations, with investments measured in trillions of dollars and acceptance of significant risks, including likely loss of life. It requires technological advances in numerous fields and development of entirely new industries and supply chains. It requires legal frameworks for space resource utilization and governance. It requires enough economic justification that continued investment remains politically viable. Is this achievable? Probably, if humanity decides it's sufficiently important and commits the necessary resources. Will it happen? That depends on decisions made by governments, organizations, and ultimately, societies over the coming decades. The moon isn't going anywhere. The question is whether we will. If we do establish permanent lunar presence, it will likely be gradual. Initial scientific outposts, slowly expanding capability, eventually transitioning to something resembling true colonies that can sustain themselves with minimal Earth support. The timeline stretches across generations rather than years. Those who begin the process probably won't live to see its completion, but perhaps that's fitting. The greatest human achievements, cathedrals, civilizations, bodies of knowledge, often span multiple generations. Those who lay foundations rarely see the finished structure. What matters is whether we're building something worthwhile, whether the vision justifies the cost and sacrifice, and whether we're proceeding thoughtfully rather than recklessly. The moon has waited 4 billion years. Whether humanity establishes permanent presence, they will say something profound about who we are as a species, what we value, what we're capable of achieving when we commit to long-term goals, and whether we can extend our presence beyond our birth world while maintaining the wisdom to do so responsibly. That's the realistic picture of lunar colonization, neither the utopian fantasy of easy expansion into pristine frontier, nor the dismissive pessimism that declares it impossible. It's a challenge perhaps at the edge of our capabilities, requiring the best of human ingenuity, cooperation, and perseverance. Whether we meet that challenge remains one of the great open questions of our time. Living on the moon captivates our imagination, but the reality involves confronting challenges more complex than most people realize. From the mundane difficulties of taking a shower in low gravity to the existential threats of radiation exposure and micrometeorite impacts, from the psychological toll of isolation to the staggering economic investments required, every aspect of lunar colonization demands careful thought and innovative solutions. Yet, despite these obstacles, the goal isn't impossible. With sustained effort, technological innovation, international cooperation, and commitment spanning decades, humanity could establish a permanent presence on our nearest celestial neighbor. Whether we should remains a question each generation must answer for itself, weighing the costs against the benefits, the risks against the potential rewards. The moon waits in the sky, just as it has for all of human history. What we do next is up to us.